We're going to try one more substitution rule problem for indefinite integrals. And this one kind of is going to show almost a worst case scenario for what can potentially not go wrong with a function, but when you don't have a lot of things matching up too nicely. And we'll see what we mean in a few minutes here. So let's integrate the function x cubed times square root 1 plus x squared. All right, so let's go through our usual process here. We want to choose u. And we can see that it's probably see what we're going to pick for u because we see a root function and then there's some terms inside that root function. So most likely whenever we see an inner function, we're most likely going to pick u to be that inner function. So I would guess u is going to be 1 plus x squared. And that's because I'm seeing it inside the root function. Now to help with our integration, let's do a few things. Let's rewrite this root function as a power function. That's going to be helpful. And then we know that this square root term here is kind of influencing our choice for u. So let's move everything else, this x cubed, let's move it over next to the dx. Not really necessary, but it's helpful to do that. So we're going to do a few things. We're going to rewrite this as 1 plus x squared raised to the positive 1/2 times x cubed dx. All right. Well, we picked u, so now our hand is forced. Now we calculate du. So what's the derivative of 1 plus x squared? Well, that's just 2x. And then we multiply by dx. And like we said, this term here, this 1 plus x squared raised to the 1/2, we know what that's going to become. That's going to become u raised to the 1/2. So we want to compare the leftover terms, this x cubed dx, with what we calculated for our differential. And we see some kind of big differences here. In our integral, we have x cubed dx. In our differential, we have only an x dx. There's this 2, but constants, we can always move constants around. So the constant doesn't really matter. We can deal with that. It's the variables that are the biggest concern. So when we look at this, we have an x dx here. So what we can do, though, is in this x cubed, we can separate off one of the x's. So separate. We want x dx. So we're trying to work with what we have. So we want to produce an x dx here. So break it up, split it up. So we'll have the integral of 1 plus x squared raised to the 1/2 power, and then x squared times x dx. Okay. So the question is, we have an x dx here. We have an x dx here. That's good. We have a 1 plus x squared here. And that's how we chose u. So that's good. So the question is, we have this x squared right here in the middle that is kind of not spoken for at the moment. So we have to figure out what can we do with this x squared term. And so we want to keep in mind our goal. Our goal is to replace all x terms. So we can't, once we switch over to u, all the x's have to be gone. So let's start switching over. So what are we going to get? This 1 plus x squared raised to the 1/2. What is this going to become? Well, it's going to become u raised to the 1/2. And then this x dx, what are we going to have there? Well, if we look at our differential, we can solve for that x dx. So if we solve for that x dx, divide both sides by 2, we get 1/2 du is equal to x dx. So that can go in right up here. And so the question is, what are we going to do about this x squared that's right in the middle here? What are we going to replace in our integral? And we have to use the pieces that we have. So when we look at this, we choose u, and then we calculate du. So a lot of times the work that we do comes around with fidgeting around with this differential, like we normally do. We've seen in a few examples where we're solving for x dx here. So we have to do a little bit of solving here. But we also have this other equation that we might have to fiddle around with. So we have this u equal to 1 plus x squared. And we want to know, well, what is x squared? So we want to know what x squared is. We have this equation, u is equal to 1 plus x squared. Well, sometimes you have to work with this equation. And so in this case, we can solve this equation for x squared. And so if we do that, we get x squared is equal to u minus 1. So subtract 1 from both sides. And that's what's going to go right in here. Because now we know x squared, based on our substitution, x squared is equal to u minus 1. All right, so there we go. We have this new integral that's all in terms of u, and we're going to have to work with this. So far it seems kind of similar in complication. You know, it's u to the 1/2 times u minus 1. It's a product here. And what we can do next is we can actually multiply all this out. So we've gotten our integral now where it's all in terms of u. So let's look at, we're doing the integral of u raised to the 1/2, what was it? U minus 1 times 1/2 du. And we want to do this integral. Now it's a brand new integral. So how are we going to do this? Well, the issue now is this is a product. It's a product of two variable terms. We have this u to the 1/2, which is a variable term, and then we have this u minus 1, which is a variable term. The times 1/2, that's a constant multiple. We can deal with constant multiples. That's not the issue. The issue is this product right here, variable term times a variable term. And so when we have a product of two variable terms, the way we deal with it, at least for right now, is to try and do the multiplication. And that's what we can do here, is distribute this u to the 1/2. So when we do that, we get the integral of u to the 3/2 minus u to the 1/2. Remember, we add exponents, so there's kind of a hidden exponent of 1 right here, and then we add the exponents to get 3/2. And don't forget the differential at the end. And now that 1/2, while we're at it, what do we want to do? We could distribute the 1/2 to each term, but just move it in front. And we're going to get the antiderivative for each of these powers. So now why this multiplication is nice is because this is just a power function and this is just a power function, and we're doing subtraction. So we can just use the power rule twice here. So what's the antiderivative of this u to the 3/2? Well, our variable is u. Add 1 to the exponent, so that takes us up to 5/2. Take that new exponent, flip it, put it in front of the u, so 2/5. And then we have minus, and then do the same thing for this u to the 1/2. Our variable is u. Add 1 to the exponent, so we go up to 3/2. Take that new exponent, flip it, put it in front of that u, so 2/3. And then plus c. And then now we can distribute the 1/2, and it's just going to cancel with those 2's. So what we end up with is 1/5 u to the 5/2 minus 1/3 u to the 3/2 plus c. And we're almost there. We're done integrating. Last step is just convert back to x. So we're going to end up with 1 over 5. And then what was u? What did we say u was? I forgot already. What was u? 1 plus x squared. So going back, we're going to switch each of those u's that we have. We're going to switch each of these to a 1 plus x squared. There we go. And then we have minus 1/3, 1 plus x squared, raised to the 3/2, and then we are plus c there. And yeah, that's our antiderivative. We got it. So that one definitely kind of showcases how involved sometimes these substitution rule problems can be. This is where almost everything, it's not the worst case scenario, but it's in that realm where things didn't match up too nicely. So we had to do some work to get our differential to match. Then we had some x terms left over, and our goal is we had to get rid of it. So we actually had to work with this other equation to figure out what x squared was. So sometimes you have to work with both of these and fit all the pieces in. And then, to top it off, the result was a product of two functions, so we had to deal with that. And the way we handle a product is the product of two power functions is actually do the multiplication. So add the exponents, and then we get it to a point where it's just two power functions, and we're subtracting, so we can just do it. All right, so a lot of examples for substitution rule, but the reason is because substitution rule is incredibly important for finishing up the integration sections in Calc 1. Going into Calc 2, substitution rule is incredibly important. And it really kind of makes or breaks your Calc 2 experience. If you can do substitution rule, you're going to have a much easier time in Calc 2 than if you're kind of struggling with it. So I want to just kind of expose you to all these examples just so you can kind of develop that practice of using substitution rule, and specifically how to choose u. That's the key part of it, is how do you choose u. All right, so don't worry, we'll practice a few more when it comes time to doing substitution rule and definite integrals. So we'll get a little more practice in. We'll see you then. Bye-bye.